We study a dynamic deformable manipulation task. We assume that the robot has already grasped the deformable object, and that the robot can accurately measure the 3D position of a single point on the object. Our benchmark task is to track a fast-moving trajectory with the measured point. The true state of a deformable object is continuous, infinite dimensional, and governed by complex dynamics. Furthermore, the system is only partially observable. We cannot measure the full continuous state from the real world, only the controls U and observations Y. We learn an input-output dynamics model from real-world data using a recurrent neural network, which has an uninterpretable hidden state, X. The recurrent network forms a discrete time dynamical system, so we can use standard nonlinear state estimation techniques to estimate a value of the uninterpretable state that is consistent with past inputs and outputs. In our protocol, we first interact with the object to build a dataset, which we then use to train the recurrent network. We estimate the recurrent network state from past inputs and outputs using an extended Kalman filter. We then use the mean of the Kalman filter belief distribution as the initial state for the dynamics rollouts in a nonlinear model-predictive controller. The controller sets end effector, pitch, and yaw angles for the robot. The Kalman filter consumes inputs from the controller and measurements of a single point from a motion capture system. We test our method on a robot arm grasping a foam cylinder. This video shows the tracking performance for a circular trajectory. We also perform an ablation study where we remove the Kalman filter component. This results in an open-loop system with no opportunity to use observations to correct for modeling error in the recurrent network dynamics. The open-loop system shows degraded tracking performance. More details and the results for other trajectories are available in our paper.